There are two methods within KYPipe for providing an out-of-network water supply to a tank: inflows and feedpipes. By out-of-network, I mean a source that we don't wish to explicitly model. The most common example of an out-of-network supply is a municipality that is buying water from another municipality. But these two features allow us to add any flow that enters a tank before being distributed to the remainder of our system. These methods only work during a KYPipe Extended Period Simulation, which is a simulation over a period of hours to days, one which proceeds at a user-defined time step. This is as opposed to steady-state simulations, which are an instantaneous look at the pressures and flows throughout the system. Inflows and feedpipes do not function for steady-state simulations because the volume of liquid in the tank doesn't change. First, we will discuss inflows. Within the Node Info window for the tank, we can click inside this field and add a flow value. The units will be the same as our global flow units, which are found in the System Data menu. In this case, we'll be using gallons per minute. To see how this works, let's look at this tank. We see the tank is not fed from any other source, as its connecting pipe is closed. If we add a value to this field and do nothing else, this non-time varying flow will be added to the tank throughout the EPS. The tank's diameter was set so that a 1 GPM input fills the tank at a rate of 1 foot of head per hour. That way we can determine if the tank is filling as we expect. Adding an inflow of 1 GPM to the inflow field, going to the Scenarios EPS tab to turn on our Extended Period Simulation, and pressing the Quick Analysis button to run the EPS. Shows the tank filling at the predicted rate. We can vary the amount of inflow the tank receives over time. First, we'll go to the Devices tab and click on the Tank Inflows button. Within this menu, there's a drop-down list which lets us select the demand type for inflows to our tank. So, what do we mean by demand type? Within KYPipe, all demands have a type. One type is residential, and there are also numbered types starting at type 1 and going up as integers from there. Often, when modeling a municipal scenario, we have both residential and non-residential demands. So, after we enter our residential demands, we might use type 1 to represent commercial demands, type 2 might be light industrial, type 3 might be heavy industrial, and type 4 might be agricultural. Let's make this a type 5 demand so it won't conflict with other demands that we might add to our model. Next, we'll go to the Demand Patterns menu. This is the Demand Patterns table. We see there is a row for type 5 demands. We can enter demand factors here, which are multipliers for the demands entered in the map area, including tank inflows, but they are applied based on case or time, depending on whether we are running a steady-state simulation or an extended period simulation. So if we enter a demand factor of 1.33 in the first column, that would be an increase of 33% for all type 5 demands entered in the map area for case 1 if we are running a steady-state simulation, or for the hour from time equals 0 to time equals 1 if we are running an EPS. Which of course we are, since, as we said, inflows only work during an EPS. However, there is a modeling convention that we need to be aware of. That is, the value entered doesn't just affect the first hour of the simulation. The value is carried forward throughout the rest of the simulation, even without the need to type it in repeatedly, unless we change it to a different demand factor. This convention allows users to set up a flow multiplier which doesn't change without having to enter multiple values. If the first column is left blank, the field is treated as if it contained the number 1, and thus all values are set equal to 1. However, this only applies if the column is blank. Any value we enter into this table is carried forward until it's changed. If we want our delivered flows to go to half of the value we entered within the tank's inflow field at 10 hours into the simulation, we go to column 10 and enter a value of 0.5. Again, this would be carried forward for the rest of the simulation unless we add another value at a later time step. This is how we can create time-varying inflows into the tank, so long as those flows can be defined by a time series dataset. One thing it's important to remember is that the global demand factor is a multiplier that works like the multipliers entered in the demand patterns table. But it applies to all demands entered in the map area, so placing a value of 2.0 in this field will double any type 5 demands, and therefore double the amount of inflow to our tank. Here's how that looks. Flows are doubled as compared with our previous run for the first 10 hours. After that, the 0.5 demand factor we entered multiplies the GDF of 2.0 by half, and the tank again fills at 1.0 GPM for the remainder of the simulation. We'll remove these inputs and go to our next example. While the global demand factor is useful for immediately looking at scenarios like peak or slack days, we need to be careful that it doesn't inadvertently change our tank inflow. But how do we separate our inflows from the effects of the GDF? This brings up the second method for delivering out-of-network water to a tank, Feedpipes. Feedpipes require more initial setup, but are also more flexible. To use a Feedpipe, first we need to change the tank to a node called a Feedpipe tank. This node is fed by the flow through a designated pipe, which must be modeled separately from the rest of the system. Here are some examples of different ways to set up a Feedpipe. According to our modeling convention, these examples are all disconnected from the Feedpipe tank. So if we use this first example, any flow going through this pipe will be added to our tank. This occurs even though this pipe is not physically connected to the tank within our model. This convention keeps it clear what portion of the system constitutes the Feedpipe and what constitutes the non-Feedpipe portion of the system. However, if your municipality is buying water from another municipality, you don't want to model the seller's entire network. So KYPipe allows you to only model a single pipe to represent the seller's entire system, although the Feedpipe does need 2 end nodes to enable the analysis. One reason for this is that KYPipe requires every element in the system to be connected to a supply node so the program can set an initial pressure throughout the system. Failing this, the program returns a disconnection error message upon analysis. However, even if it wasn't a requirement for all nodes to connect to a supply node, the Feedpipe needs a pressure supply to generate flow. It also needs a way for flow to leave the pipe, so 2 nodes are required to complete the setup, one to deliver the water at the upstream end, and one to accept the water at the downstream end. After we have the Feedpipe set up, we go back to the Feedpipe tank node, and within this field in the node info window, we enter the name of the Feedpipe. The first Feedpipe example is the simplest, consisting of a reservoir and a junction node with a demand. The demand node draws this user-designated amount of water through the pipe from the reservoir. Similar to the inflow we set up initially, we can create a Type 5 demand at this node. But unlike the inflow feature, we can skip the step of setting the inflow type within the Devices tab. Instead, if we wished, we could go straight to the Demand Patterns menu to vary the flow to the tank with time. However, with the exception of skipping the inflow type, this Feedpipe uses the same basic mechanism as the inflow, that is, it relies on a demand value entered in the map area. So the global demand factor still affects the amount of water the tank is receiving. But Instead of using the demand patterns table, we could alter the demands at the junction node over time by using the node changes table. This produces flow in the feed pipe that is not affected by the global demand factor. This happens because changes entered here are absolute. Another important characteristic is that these changes are only valid for the time or case they are entered for. Unlike the demand patterns table, KYPipe does not carry over demands entered in the node changes table to the next time for extended period simulations or case for steady state simulations. The node changes table was created this way to allow the user to set up temporary demands, such as fire flows, which automatically expire at the start of the next case or time, as we can see in the graph. For example, let's say a sister municipality can sell us 700 gallons per minute, except during the hours of 3 p.m. to 8 p.m., when they can only sell us 400 gallons per minute. First, we'll go back to our junction node and change the demand to 700 GPM. Then, in the node changes table for this junction, we'll enter the changes to lower the demand from 700 GPM to 400 GPM for the 5 hours between 3 p.m. and 8 p.m. for each day of the simulation, and let's run the simulation for 2 days. I've already created these changes for the 48-hour period, so I'll load them from a change data file for this node. We can see the changes we've loaded within the graph. I'll also increase the tank diameter, since if it fills entirely, KYPipe will treat it as a closed node, which can generate a disconnection error. Disconnection errors can happen downstream of closed nodes or pipes, because the software must be able to calculate the initial pressure at each node, as we discussed earlier. Now we can analyze the model and see if the flow in the pipe looks to be correct. The flow is correct, although the graph draws the flow trace with slightly angled lines. The slightly angled lines are an artifact of the way the graphing application works. The lines are actually either all vertical or horizontal, as we input them as a step function, which we can see by looking at the results data table. We see the flow changes from 700 to 400 with no intermediate flow value. However, while this reproduces our target flow in the feed pipe, some of our flows can still be affected by the global demand factor. That's because the entries we made in the node changes table only affect the flows for the hours between 3 p.m. and 8 p.m. The flow for every other hour of the simulation was set at the demand node in the map area at 700 GPM. So we see that doubling the global demand factor still doubles these other flows. Here we'll press the Show Previous button to see the difference. To correct this, we can go hour by hour and override the initial flow in the node changes table. That way the flow in the feed pipe will always be independent of the setting at the demand node within the map area. This type of setup involves more data entry, but there's a way to reduce the amount of work involved. Within KYPipe, we can go to the data tables, click the All button, click Yes, and then go to the Node Changes worksheet. The data tables function very similarly to a Microsoft Excel spreadsheet, so we can create and edit node changes here more easily than we could within the Node Changes table. I've already created the needed changes within Microsoft Excel. Copying and pasting these resets our flows to the desired values. Now, if we return to the Node Changes table, we see that the global demand factor of 2.0 no longer doubles any of the flows, which start out at 700 GPM and drop to 400 GPM during our 5 peak hours. Here is another type of supply control arrangement for a feed pipe, namely a variable pressure supply whose flow is regulated by an active valve exiting to a reservoir. Active valves are used to represent standard valve types, such as butterfly, gate, ball, and needle valves. The active valve node is different than on-off valves, which will either keep a pipe fully open or fully closed. Conversely, active valves can be all the way open, all the way closed, or open to any extent in between. Active valves allow the user to input a stem position for the valve called the initial ratio, which determines the valve's open area based on the valve type. For instance, at a stem position of 0.4 or 40% open, the open area of a butterfly valve is 0.191 or approximately 19% open. We can use the Node Changes table to vary the stem position, and thus the open area, of this valve to reproduce the two different flows needed. We would need to iteratively test the valve with different stem positions until we achieved the flow rates we wanted, and then input these values. I've already done that testing for purposes of this video. So we'll set the valve's initial stem position to produce a flow of 700 GPM. And next, we'll enter the valve setting that produces the 400 GPM flow in the Node Changes table at the appropriate times, after which we'll bring the flow rate back up to 700 GPM. Again, I've created these changes and saved them to a change file. So I'll load them, save them, and set the feed pipe to P58. Then we'll press the Quick Analysis button to start the EPS. This produces the same results as using the Demand Node option. Again, we see angled lines within the graph, not vertical lines, but the flow data points are correct, as we can see in the results table. Since we used active valve stem settings, not demands, these flows are not affected by the global demand factor. This last example consists of two unbalanced reservoirs whose flow is controlled by a regulator, specifically a flow control valve. We have fewer options for this type of feed pipe, since regulators can't have their settings altered from within the Node Changes table. Their settings are static for the entire simulation. Therefore, we can't change the flow control valve setting from 700 GPM down to 400 GPM and back up to 700 GPM. However, we can still make this control type function correctly if we add some nodes and pipes. We could create a situation like this, with two sets of paired reservoirs and regulators, upstream of our feed pipe. The first reservoir regulator combination allows a flow of 400 GPM through the feed pipe. The second pair allows a flow of 300 GPM. Our feed pipe is pipe P61. Within the node changes table, we leave the first pair open continuously and start the simulation with the second pair open, but turn them off between the hours of 3 p.m. and 8 p.m., dropping our flow from a sum of 700 GPM down to 400 GPM. Then change the feed pipe to pipe P61, and press the Quick Analysis button. We see this method also produces the same results as using the demand node option. Again, if we look at the results table, we see this is a step function with the flow values changing from 700 to 400 and back again. This control method relies entirely on static regulator settings fed by pressure supplies, which are turned on and off in the node changes table, instead of relying on a demand in the map area. So, like the last two control methods, it's not affected by the global demand factor. These three examples demonstrate ways to model a time series input of water to our tank. But what if we have the situation where we receive water only when a switch is activated at a sensing node? An example would be if we buy water from another municipality when our tank reaches a low switching level and stop receiving water when our tank reaches a high switching level. Feed pipes can accommodate this type of input control as well. Let's model an example where our tank starts to fill at 500 GPM when its depth falls below 1 foot and stops receiving water when its depth exceeds 10 feet. We'll go to the EPS Scenarios tab, and within the Control Switches menu, I've set up this control switch, which is currently off. We'll turn it on by clicking in this field. This switch turns on reservoir R2 when the water level in the tank is below 1 foot, and closes the reservoir when the water level is above 10 feet. Let's set the feed pipe to P1 back at the feed pipe tank, then run this analysis. We see the tank filling until it reaches the appropriate hydraulic grade. This summarizes the multiple ways in which users can set up a feed pipe. There are also a few further considerations to mention. The first is that analyzing a feed pipe system for the first time after opening the software causes KYPipe to return a warning that the model contains disconnected pipes. It's important to realize that this is not a disconnection error message. It's only a warning. As we said, the feed pipe must be separate from the main system. Thus, so long as all disconnected nodes have access to a pressure supply, we can click OK, and the file will analyze without returning actual error messages. The second consideration is that feed pipes only transmit positive flows within the pipe to the feed pipe tank. Pipe flows are defined as positive when they travel in the direction in which the pipe was laid out, and negative if they travel opposite the direction in which the pipe was laid out. For instance, this pipe was laid out from the regulator to the reservoir, and this system only flows from left to right. Thus, the flows through the pipe are always positive. However, in the situation where this pipe was laid out in the opposite direction, it wouldn't function as a feed pipe, causing the flow into the tank to equal 0. To fix this, we would need to alter the pipe's direction by clicking on either the first node field or the last node field to bring up the Pipe Connections menu. Within this menu, we would click on the Reverse Nodes button, and we would see that the labels for the first node name and the last node name were transposed, indicating that we had successfully reversed the pipe direction. This is what that looks like. However, we'll cancel the change since this pipe was laid out correctly to begin with. The last consideration is how to track the flow through a feed pipe. This is something the program can do for us, using this node, which is an inline meter. Now we'll look at the analysis report. Within this drop-down menu, we can see a report for any time step in the simulation. If we scroll to the bottom, we can see a report for the final time in the simulation, which occurs at 48 hours. We can scroll to the bottom of the 48th hour report and see the cumulative volume that flowed through the inline meter. Inline meters actually record net volume, so if there are any flow reversals, that amount would be subtracted from the total. So, if this is not taken into consideration, inaccurate results could be obtained. However, feed pipes only contribute flows to their tank in the direction in which the pipe was laid out, and the setup methods shown above only produce unidirectional flows. So the inline meter always records correct data for these types of scenarios.